right, you've made it to the first video for Math 96 online. In this video, we're simply going to review the concept of linear equations. The expectation is that you've seen linear equations before. Again, this will be a quick overview of these four examples right here. We're going to tackle a basic two-step linear equation, and then a two-step linear but with fractions, which can make it a little bit more difficult, and then these multi-step linear equations. If at any point you need some more examples or more explanation for any of these problems, know that many of the problems has videos linked to them, or you could back out of the homework or in another tab, look at the textbook sections that are listed as PDFs below. Let's tackle this first problem. 7x plus 1 equals negative 41. We're looking to solve this equation, which means to find the solution. The solution to this equation is the value of x that we can plug in that makes these two sides equal. In this case, since this is a simple two-step linear equation, meaning there's only two different operations happening to our variable here, we're trying to get this side to equal negative 41. While you might be able to guess the solution, the easiest way is to do what I call reverse engineering of the operations. In this case, our x is being multiplied by 7 and then has 1 being added to it. What we can do are do the reverse operations in the opposite order. In this case, meaning the first thing I'm going to do is subtract 1 from both sides of the equation. That leaves me with a 7x because this plus 1 and the minus 1 cancel each other out. And on this side, negative 41 minus 1 is negative 42. Then what I'm going to do is divide both sides by 7. I'm dividing by 7 to undo this multiplication of 7 right here. That would leave me on this side with just an x equals negative 42 divided by 7 is a negative 6. Again, before I move on, what this solution is the value for x that I could plug in to the original equation to make this side equal this side, or to make this side, in other words, equal negative 41. Before I move on to the other examples, I just want to hit on this idea of a solution, specifically for 3 and 4, these multi-step linear equations. What I'm looking for is the value of x that I could plug in here and here, and here on both sides so that the values of these two sides of the equation are equal. In my second example here, I just want to talk about having fractions in linear equations. If you're a normal person, anytime you add fractions to a problem, it can become significantly more difficult. What I want to show you or remind you of is this concept of clearing fractions. We are allowed to, at any time, to multiply, divide, add, or subtract anything that's the same to both sides of these equations. In this case right here, what I'm going to do is I'm going to multiply a number that's a multiple of all of the denominators I see in my problem. In this case, I'm going to multiply every term by 20. If I multiply every term by 20 in this problem right here, I'll get an equivalent equation that has the same solutions, but then no longer has fractions. All right, and just to review that, I'm multiplying by 20 because 20 is a multiple of all these denominators. And what that means is when I multiply 20 by 1/5 and 1/4, because this number is a multiple of these denominators, the result of that multiplication will be an integer or a whole number. So I won't show all these steps, but you can verify this. When I multiply this 1/5 times 20, I'm going to get a 4. So this first term becomes 4x. And then 20 times the 1/4 here using distribution, this will give me a plus 5. And I have to multiply this negative 1 by the 20. Also, that gives me negative 20. And before I finish this problem, I've made this significantly easier. I want to make two really important statements. First, I don't have to use this move of clearing fractions. I could have instead subtracted 1/4 to both sides and divided by 1/5. Though usually doing operations with fractions can just make things a lot more difficult, it's much easier if I use this trick of clearing fractions. I'll then get an equivalent equation. Importantly, the solution to this equation is exactly the same as the solution to that equation, because anytime I multiply everything on both sides by the same value, I don't change the solution. And so here now, all I'm going to do is subtract 5 from both sides of the equation. This gives me 4x equals negative 25. I'm then going to divide both sides by 4, getting my solution, canceling that multiplication of 4. I get that x equals negative 25 fourths. Also, to make the note of something like this, especially in this class, if I take a number like negative 25 and I divide it by 4, you could put that in a calculator and get a decimal approximation, but the easiest way to answer is just by saying negative 25/4 here. Also, we don't use mixed numbers, so you wouldn't say something like negative 6 1/4. Leave it as an improper fraction. Next up, we have multi-step linear equations. And importantly to this conversation, for both these last two examples, if you want to see more support or more examples of these, look in the multi-step linear equations sections, or you can even Google that topic for lots of more examples. The issue here, the difference being, is I have instances of my variable on both sides of the equation, and specifically on the left-hand side here, I have more than one instance. The rules for this are pretty straightforward. First of all, I'm going to simplify both sides of the equation as much as possible. In this case, that's simply combining like terms. The only thing I can do is combine the 6x and the negative 14x together to get a negative 8x. I'm just adding their coefficients of 6 and negative 14 to do that. And actually, I only have now one more step to do before I can just employ my same strategy for number 1 and number 2. Now that I have simplified both sides, I need to consolidate the variable. What I need to do, what that means, is to get the variable x just to one side of the equation. And what I'm going to do that is to add or subtract a certain number of x's to zero out the x's on one side. What I'm going to choose to do in this case is I'm going to add 2x to both sides. I'm going to add 2x's because it's going to cancel these negative 2x's, but I have to add 2x to this side of the equation as well. And again, what that does is negative 8x plus 2x gives me negative 6x, because negative 8 plus 2 is negative 6, plus the 28 here. On this side of the equation, this is why I added 2x, I can cancel these 2x's together. I get 0 x's, and then I get negative 20. There's no tried and true rule for how you go about doing this, but I always cancel the x's from the right-hand side just because I like having my variable on the left-hand side, though that's not necessary. Now I can simply employ the move I did in the first two problems. I have a two-step linear equation. I'm going to subtract 28 from both sides and then divide by negative 6. Dividing by negative 6 cancels this multiplication of negative 6. And what I get as a solution is x equals the result of negative 48 divided by negative 6. That's actually just 8. Just to emphasize this one more time, what this means when I say x equals 8 is a solution to this equation, this means 8 is the value that I could plug in here, here, and here at the same time, and that will make both sides of these equations equal to each other. And the steps I used to accomplish that were simply first simplify each side, then do this move of consolidating the variable, which will leave me with a two-step or one-step linear equation, depending on how many terms I have, and I can simply solve using these earlier techniques. For this last example, I'm going to employ exactly the same strategy from previous. What I'm going to do is simplify both sides of the equation and then consolidate the variable. In this case right here, I have a bit of work to do. I need to distribute this negative 9 first. That'll give me negative 54x plus 18 plus 8 equals, and then this side, there's no simplifying to do. I just get negative 54x plus 30. Next, I'm going to just combine these like terms to give me negative 54x plus 26 equals negative 54x plus 30. Now, I'm going to consolidate my variable. I do this by zeroing out the number of x's over here. I have a negative 54x, so I'm going to add 54x to both sides. This last example is a type of equation that we either call a contradiction or a tautology or an identity. In this case, these types of equations have an issue when you try to consolidate the variable. If you notice in this case, I had negative 54x's on both sides of the equation. When I go to consolidate my variable then, I don't only cancel my variable on one side, I cancel it on both sides of the equation. This is a really crucial step, and at this point, I don't know the actual solution to this equation yet. But what I do is I let the x's get canceled on both sides, and what I have now is the equation of 26 equals 30. You'll notice there are now no x's in this equation. That means I cannot solve this for a unique single solution. In this case, if my variable cancels from both sides, I have either an equation that's an identity, which has infinite solutions, or any real number is actually a solution, or I have a contradiction, which means that no value works. In this case right here, what I'm left with is a false statement. We all know that 26 is not equal to 30. If my variable cancels and I'm left with a false statement, it means there are no solutions. Anytime in WAMAP I have an equation or I'm trying to solve something that does not have any solutions, I'm going to answer with D and E for does not exist. Last thing to say about this, again, you can see examples of this in the textbook. If I had done these exact same moves, but this last statement right here was actually true, what that would mean is there are infinite solutions or any real number works. And just to clarify that real fast, what that would mean is that any value I plug in for x here and here would make both sides true. We call that an identity because it means that actually both statements must have been actually exactly the same. In this case, it's not a true statement, so what that means is there is no value that you could find to plug in x here and here to make these two equations equal to each other. And to finish that thought, if it was true, I would say there's infinite solutions or all real numbers. In putting into WAMAP, I would make two little O's, which means the infinity symbol.